Thank you so much for that introduction. I really appreciate it. And thanks everybody for coming. Can you hear me reasonably well?
Yes.
Yeah, okay, great. I'm going to talk about something that I don't want to talk about and you don't want to hear, but we have no choice. And that is how we protect our data to make it available. We have been protecting our data for decades, but the way that we're doing it is no longer adequate. It's easy to break. Privacy can be violated. Privacy protections can be easily violated. We really don't want to hear this. The computer scientists have basically ruined our day because we had this good thing going about how to share data. However, it is important to realize that the flow of data into our field has been extraordinary. A few generations ago, our predecessors in the social sciences, all they did is study things. They studied this and then they studied this. We actually solve problems. We make discoveries. We have inventions. We learn about the social world in ways that can be actionable, that are turned into public policies. It's actually, like, if you look across the decades, this is actually a great time to be a social scientist. It's one of the most dramatic areas, but it depends upon having access to data. It depends upon the way that we fairly share data. And it turns out that doesn't work anymore. So let me give you an example, a big example that I was involved in. And I'll show you the problem. What I think we need to do, the way that we need to solve these problems, and many political problems really, is solve political problems technologically. So that's sort of my pitch, to try to solve the political problem of data sharing technologically and other things. So I want to solve political problems technologically. The way that I'm going to talk about how to share privacy is now, there's a reasonable consensus in the academic literature, which is called differential privacy, which I'll explain to you what that is. And then I'll give you an example of it and show you how it works in practice. But first, I want to tell you the story about how I managed to convince Facebook to make some data available, because although we have more data than ever before in academia, we have a smaller fraction of the data about the people that we study than ever before, because most of it now is tied up inside private companies and inside governments and inside other organizations. And unless we can assure everybody that we can really protect their privacy, we're not going to be able to continue to have access to it. So I'm trying to convince Facebook to make data available. I'm going to give you first an example of how we solve a political problem technologically by constitutional design or something like that. So I would go out to Facebook and in Menlo Park, California, try to convince them to make data available. I made lots and lots of trips over lots of years, and it wasn't very successful. On this particular trip, I was in my hotel room packing to go home, and I get an email from the people that I talked to at Facebook, and they say, "Hey, what do we do about this?" And this was Cambridge Analytica. Cambridge Analytica was this enormous privacy violation where it was an academic that had access to a vast amount of Facebook data and just handed it off to a private company. And so it was the academics that were violating privacy. So this was an example of the worst time lobbying event in pretty much the history of the world. It was really crazy, right? And so, I wanted them to make data available to an academic who I said could be trusted, but it turned out that all academics can't be trusted. So I went home and I thought, it's fine. I made lots of other trips, no big deal. Visited my daughter, who at that time was an undergraduate at Stanford, no big deal. 3 days later, Mark Zuckerberg called and he said, "Gary, could you do a study of the 2016 election for us and explain to everybody that we didn't change the outcome? Or maybe if we had an effect, tell us what it was and we'll change whatever it is," right? Losing $100 billion in market capitalization sort of focuses the mind. That was my impression, right? So I said, "Okay, so Mark, I would love to do this study, but I need two things, and I think you're only going to give me one thing, but I need two. So you give me two, I'll do it." I said, "Here's the two. first I need complete access to the data, of course, and the people and the platforms and the policies and everything you're doing. He said, sure, of course, we give employees that, no big deal. I said, okay, but we also need a second thing, which is no pre-publication approval of what I write by the company. Because if the company can filter what I can write for the world, then nothing that I actually do publish would be of any use to the scientific community. I said, I want both of those things. And he said, you're right, I can't give you both of those things. I said, well, okay, Mark, I'm not going to do the study. And he said, well, no, but we really want you to do the study. I said, okay, give me both of those things. He said, well, no, we can't give you both of those things. I said, so, okay, we're not going to do the study. So we went back and forth until I finally said, wait a second, there's a solution to this. We're going to make it a two-part solution. I proposed a two-part solution. I said, first, we're going to have outside academics send in proposals with no company veto. So the company gets no veto, but the proposals have to be vetted. The company doesn't get to vet the proposals. Instead, there's a trusted third party, a bunch of academics, senior distinguished academics, who take one for the team and agree not to publish, but they get inside Facebook. They are told some of the secrets of Facebook. So if there is a secret lawsuit about a particular subject and an outside academic proposes to study something that is meritorious from an academic point of view, but would subject that person to deposition because of the secret lawsuit, then we will just say, sorry, you can't have access. We won't explain why, and it'll be too bad. But we stand up. The trusted third party of academics would stand up for the outside academics and would stand up for Facebook. And so this actually worked. Okay, so this was sort of like constitutional design. And Mark said, okay, the problem was solved. No balancing the two interests. Everybody got 100% of what they wanted. We had legal agreements, took us a long time to write those out, figure it out. We had big announcements. Mark Zuckerberg testified before the United States Congress and talked about this project. We got funding, like $11 million of funding from outside foundations that joined in. Facebook assigned more than 30 people to our project. It was great. It was really terrific. There was only one issue with this. And the one issue with this was that what Facebook was planning to do, the way that they were going to share data was, well, illegal. And, to be fair, they didn't know that it was illegal when I came to this agreement with Mark Zuckerberg, but it was illegal. And because basically, like we were going to, the idea was they were going to give us access to the data, but who said that we could have access to the data? The regulators said, hey, you're not going to do that. They can give the employees access to the data because if they do something wrong, they can fire them. But they had no leverage over us, which wasn't the point. So now we had a new problem. How does Facebook share data with academics outside of Facebook without the data actually leaving Facebook? So it was like, again, we have to do something that we need. We have another sort of political problem. And so how do we solve this? So we're going to solve this with this data sharing solution. And I think it's not just Facebook. It's actually quite general. The Facebook project produced a data set with 40 trillion numbers in it. So it was successful, and eventually we got access to academics. And if you would like access, go to socialscience.one. That's a website, socialscience.one, and there's a particular procedure by which you can get access. But that's, I think, probably the largest social science data set ever constructed. It's a differentially private data set, which the subject for which is going to be the rest of my talk. But this particular solution here, the way that we managed to share data without leaving Facebook, is much more general. So the much more general point is that we're going to be switching, I think, all of us in academia, whether we like it or not, are going to be switching from a data sharing regime to a data access regime. So let me explain what these are, because it's very important. It solves another political problem technologically, this time by computer science and statistics. So the data sharing regime is what we've been doing for a long time. You want data from me, you call me up, you say, I'd like your data. I say, here's my data. or we put it in Dataverse and you download the data. Maybe you sign a data use agreement or something like that. That's the data sharing regime. It almost always works. It just doesn't always work, and there's no guarantee that it will work. Then there's a data access regime, which is this new thing that I'm going to describe. Okay, so the data sharing regime is venerable, but it is failing. We don't want to pay attention to this, but it is failing. There's increasing public concern all around the world among citizens and among regulators with privacy. Scholars have discovered that de-identification, which is the main method we have used for a long time to protect the identity of our survey respondents and our research subjects, does not work. You can de-identify, but we can re-identify. It is not hard to re-identify. In fact, other methods don't work also. When we use a lot of these, if you aggregate the data to a higher level, you think, well, you can't re-identify individuals. Turns out that's not always true. Or query auditing, we limit you to certain questions. That doesn't protect individual privacy. Data clean rooms, which I know you all use a lot, that doesn't protect privacy. Legal agreements doesn't protect privacy. Restricted viewing of certain types of parts of the data doesn't protect privacy. Paired programmer models doesn't, et cetera, et cetera, et cetera. In fact, even they've proven that trusting researchers who are trustworthy, I mean, well, first of all, we know trusting researchers fail spectacularly at times. That's what Cambridge Analytica was, that's CA. But in fact, the computer scientists have proven that trusting a researcher who is known to be trustworthy can also fail. So we need something else. Basically, the data sharing regime is us academics saying to our survey respondents, we will try hard to protect your privacy. The data access regime is different. Instead of us promising to try hard, we realize it's not about us, it's about the respondents. Instead of that, we provide a guarantee to the respondents that no one can ever violate their privacy. So here's how it works. A trusted server holds the data. Researchers are treated, unfortunately, as adversaries who may want to violate privacy. We allow the researchers to run any method producing any answer, any type of estimator, but they get a noisy answer. So in other words, on the server, it calculates whatever you want it to calculate, and it adds some noise to it. Does some in very specific ways. You can only do it a limited number of times, otherwise you'd average away the noise, of course. Right? The goal, here's the goal, to make it mathematically impossible to violate individual privacy, but still possible to discover population level patterns. That's the question. Can we do that? And differential privacy actually solves that problem. It makes it impossible to violate individual privacy, but possible to discover the questions that we care about. Because we're social scientists, right? We don't care about anybody. We only care about everybody, right? We care about the patterns, not about discovering individuals. And this, it turns out, seems to satisfy regulators all around the world. I know because we've talked to a lot of them in trying to get the Facebook data approved. But it turns out there's so differential privacy will solve this problem. And it's quite a remarkable invention, I think. It will solve this problem. It will provide guarantees to respondents rather than promises that we're going to try hard. However, there's a new problem. And the new problem is most differentially private algorithms, although they do protect privacy, they are invalid statistically. So that's what I hope to change. They have unknown statistical properties. We're going to figure out the statistical properties, correct the biases. They don't come with uncertainty estimates. We're going to provide uncertainty estimates. With all of this, with differential privacy that will protect the identity of respondents and the values of their variables, and statistical corrections, we will be able to estimate any quantity that we would have estimated before without differential privacy. But we'll use different methods, and we will get pretty much the same kind of answer with somewhat larger confidence intervals. If we have a larger sample, we're good. That's the solution, and privacy will be protected with guarantees. Okay, so now let me explain to you what differential privacy is and how we're going to add inferential statistical validity to it. All right, so here's a bunch of people: Ria, Adele, Carolee, Connor, and then our co-authors, Georgie, Gary, Meg, Aradeep, et cetera. There's a bunch of people. Let's take their mean income, which is probably not $48. We have a big population of people. We then take a sample. This is the way we normally do data collection. We take a sample. Some of these people we observe, and quite a lot of people, of course, we don't observe. Here's the answers. They go into our database. We know the income, the actual income of these people. We might take the average of these. The key is that this is the truth, and that we want to learn, and this is some function of the sample. And the most important thing that I think that we all understand is that we care about this. We don't care about the answer to any question in the survey. We don't care about the people in the survey. We don't care about the averages of the numbers in the survey. We're only using the survey for the purpose of estimating the quantity of interest in the population, right? Everybody on the same page there? That's classic statistical inference. That's what we do. We collect samples, not to learn about the samples, but to learn about the population. Okay. So now along comes computer scientists, and along comes the privacy problem. And we look at this column here and we say, uh-oh, now we're going to have to treat that as private. And so in my slides here, it gets embarrassed, that column, and it turns red. Okay, see, that's a pre-programmed joke, right? And so now the data in the database of our survey is not, can't be revealed to anybody. And so we have to protect it. How do we protect it? Well, we're going to add noise, and we're going to do some censoring. Really large values we're going to cap. Okay, I'll explain exactly how we do that in a minute, but roughly that's what we're going to do for now. And then when we do that, we get a bunch of new values. These new values these are not the incomes of these people, right? They're the incomes of these people plus some noise and censoring. Okay, so if you looked at these, even if you could say, oh, this is Connor's number, it wouldn't matter, because you have no idea what the actual number is. You just see this number plus noise. On the other hand, if you wanted something simple like the average of in the population, you could average away the noise and you could estimate that, but you wouldn't be able to know any individual. Here's the problem. The computer scientists who develop differential privacy, they think about this as just trying to make an inference back to this database. It's like a query response system where you just want to make a query of your database and you get the answer. That's like the whole thing. That's their inference. That's their model of inference. We have a database, we ask for the answer, it gives you the answer, you're done. That would make statistics very easy. And since the database is private and there's noise and censoring and they only get to see this, what they're trying to do is make an inference back to what they would have had if they could see this. However, as social scientists, we don't care about the data in the database. We care about the population. We certainly don't care about the differentially private numbers, right? Because that was the numbers we don't care about plus some noise, right? That there are just no direct relevance. They're of indirect relevance, of course. What we care about is using these numbers, which is the only thing that will be disclosed to the public, to infer all the way back to the population. So that's the statistical problem that the computer scientists haven't really paid attention to, and that's what my co-authors and I are going to try to add here. We're going to use we know that if we add differential private noise in this way, we will absolutely protect individual privacy. If you use the methods I'm going to describe here, we will also protect statistical validity, and we'll be able to get whatever estimates of whatever you want from the population. Okay, everybody roughly on the same page? I will look at all of the non-videos and imagine they're shaking their head. Oh, thank you, Cindy, for that thumbs up. Okay, so let me show you different places that we could add the noise, just to give you a feel. So here's an abstraction of a survey, of the survey process. So we start with survey. It goes to a respondent. The respondent answers some questions, goes to probably their cell phone or an interviewer's iPad or something like that. Data goes into the server goes to the researchers. The researchers, of course, all wearing their caps and gowns, of course, like we always do. And then that goes to that goes to they process it and produce publications. Okay, so you can add data at each of these points. After the researchers do their analysis, we could add noise before they publish it. If you don't trust the researchers, which we're not supposed to anymore, it could be that the researchers go to the server, ask for information, and noise is added here at point 4. Perhaps you don't trust the server itself. You could add noise going into the server. Perhaps you don't trust the server and the communication method. Well, you could put the question on the respondent's device after the respondent answers the question on the device, and before it is sent up to the server, there could be noise added there. Or before the respondent puts the data into the device, we could have them spin a spinner or flip some random number, and we could ask them, if the random number is green, tell us the truth, and if it's red, lie to us. Okay, and we don't get to know whether it's green or red because it's a random number that the respondent is actually flipping. This one here, is known as randomized response. Have you seen randomized response before? It's a cool little trick where you can completely anonymize individual respondents' answers. So you can add in very sensitive, you can ask them, private sexual questions, or in authoritarian countries, you can ask them what they think about the government. I did this in my daughter's 6th grade class, and we figured out the fraction of students in the class that liked somebody else in the class, even though nobody was willing to say that, of course, right? And so that's randomized response. This goes back a long way. It turns out differential privacy is a generalization of randomized response. Today I'm going to focus on 3, 4, and 5. So there's one method that will deal with 3, 4, and 5. There's other methods that we've written about that can deal with 1 and 2. Okay. Okay, so differential privacy, let me define it for you so you have a little more precisely. In statistics, what we do is we have some data set D, and we take some function of it. That's a statistic, right? We take the mean of it, or we take a regression coefficient or a logit coefficient, anything you want. That's this, S of D. Okay. In differential privacy, DP, we have what's called a mechanism, which is like a statistical estimator. And what you do is you do something quite like this, except in the process of calculating the mean or calculating your regression coefficient, you add noise and censoring in a particular way in order to satisfy the precise definition of differential privacy. You have to prove this, so people prove this, okay? So let me tell you what the precise definition is. But when I do that, let's understand here that the noise and censoring, the precise way that we're going to add noise and the precise way that we're going to do censoring are the things that ensure privacy. And there are also fundamental problems for statistical inference. You take our data and you mess with it, you add noise, you slap down the big values. Of course, that's going to add bias. We're going to have to deal with that. Okay, so let me give you a simple version of the differential privacy standard. Let me just explain this, and let's get a feel for it. Okay, so we're going to have the data set D, which has your data in it. And we're going to have another data set D prime, which just has your row deleted. So you're one of the respondents, okay? And the question is, what are the inferences we're going to make from those two data sets? And the answer is, under differential privacy, the answers have to be pretty much the same. Whoops, sorry about that. The probability that you get from this mechanism, same thing as up here, is the probability that you get some value M with you in the data is going to be roughly the same as the probability of getting the same value M without you in the data. So the ratio of those two probabilities is roughly 1 plus or minus a really small value epsilon. Okay, so that's the differential privacy standard. In words, it means if you're in the data set or you're not in the data set, I'm going to get basically the same answer. Okay, so, and if that's true, then I think you would feel safe giving me answers to your survey questions. Okay, the examples, the ways that you develop your estimators are all designed to protect the biggest possible outlier. Okay, so that's what has to happen. So if Bill Gates is in the data and you're taking the mean, or if he might be in the data and you're taking the mean, then that's going to really mess with the mean. If you add random numbers, you're going to have to add really, really huge random numbers. If you censor the data, maybe you don't have to add as large random numbers. Okay, here's one estimator just of the mean, the average, but a differentially private average. I'm going to explain this to you. It's going to be pretty much the only equation that is complicated, and it's not that complicated. Okay, so this 1 over n times the sum of something, if the only thing here were y, then it would be the mean. Instead of y, we're taking c, the censored value of y. Anything above an arbitrarily chosen value that we will choose, lambda, will be censored. So we're going to take the average income of everybody, but anybody above $300,000, we're going to censor it and back down to $300,000. And then we're going to add randomly drawn noise, mean 0, right? So it doesn't go in any particular direction, but with a particular variance. The particular variance was derived, and this whole formula was derived in order to meet this definition. So I'm not showing you the proof of how to do that, but you'll believe me that they've proven this. So just intuitively, how much noise do you have to add? Well, if n is really large, and your data are submerged in a sea of many, many people, then the variance here can be smaller, right? That's good. If epsilon is really, really small, so you're not willing to leak almost any privacy at all, then the variance is going to be bigger. Remember I said we're going to censor? If you say, well, censoring is going to bias your data, so let's make lambda really large so we don't censor anybody. Well, that's fine, but then you're going to have to make, it's the same lambda that's here, so the variance is going to be, the variance of the noise is going to be really large. So this whole thing was worked out, so you'll get a noisy censored mean, which is differentially private. It does protect privacy in this very specific way. No matter what, you're going to get the same mean roughly with or without your data. And this is the way you do it. Okay, now I went through this with some precision because we're going to generalize from this mean to any other estimator you want by turning all those estimators into a mean. There's plenty of other very precise ways of developing different estimators that are mechanisms that are differentially private for every statistic out there. And there's lots and lots of articles trying to prove this for logit coefficients and all kinds of crazy things, all the crazy things that we do, right? They work on all of them. But every one is different and would require us to learn a whole range of all kinds of stuff. Instead, my co-authors and I have this way of using this very simple mean, which will be useful no matter what your estimator is. So it'll be simple. Okay. The statistical properties of this kind of stuff, unfortunately, is usually biased and doesn't have any uncertainty estimates. So we'll have to fix that. Okay. All right. So now let me give you our general purpose algorithm that is also statistically valid.
Very quick question, if I may. Sorry to interrupt you. So does this work for any type of statistics? So say that I want to have the maximum or the minimum, and say I want to, say Bill Gates is in the data, and if I want the maximum, order does matter for that type of statistic. So how does order count into this?
That's a very good question. When I said it will work for any statistic, it's any statistic that meets our regularity conditions, and that one doesn't. I can give you the precise answer of what meets our regularity conditions. It's too complicated for a talk. But the vast majority of things that we would normally have as in the final tables in our papers would be included here. But you're right, there's ways of getting around it, and that's a good example, right? Anything that can be amenable to a mean in the following way that I'll show you.
Some kind of an aggregation would usually work here, right? But as soon as we don't aggregate, we could probably retain, as you were alluding to, that original value. Yeah,
that's right. There is actually a way to even get the maximum, but it's much harder. I mean, estimating a maximum is always harder, but it's even harder in this case. So, okay. So a general purpose statistically valid differentially private algorithm. Okay. So let me give you an analogy. What we're going to do is we're going to divide up or partition the data. So I'm imagining the data is a loaf of bread, and we're going to partition it. We're then going to we're then going to do the same thing within each partition. First, we'll scale up that one partition to something that looks like the original. And there's this thing called the bag of little bootstraps that does that. In each simulated data set or partition of the data set or piece of the data set, we're gonna have an estimator, whatever estimator we want with Adele's qualifications. And then the estimator, some of them are going to be really large, so we're going to censor some of them. Then we're going to average some of them. That average doesn't look very good because it doesn't look like these guys because there's some that are censored. Then we're going to mess with it further and add noise, and it looks like something completely different. But then we're going to bias correct and get back to the thing that we care about, which are these things. Okay, so let me show you a mathematical version of this. We have the data D. We're going to have partition D1, D2, D3, D4, D5. For now, the bag of little bootstraps we can ignore. Each of our estimators is going to be calculated within each subset of the data. This could be a logit coefficient. This could be a mean. Whatever. Almost anything that you would care about would be here, but not everything. If there's a possibility that there's one big outlier in the data, and we need to protect that person, then we add censoring. That's what this stuff looks like. And here's the trick. This equation looks quite like the previous equation that I showed you for the mean, but there's no mean here. This thing could be, as I said, a logit coefficient. So what's happening? Well, what's happening is we're going to apply the mean to the average of these things. But instead of averaging, we're going to have a differentially private average. So it's going to be a differentially private average over the partitions instead of over the observations. So this equation looks like the previous equation. This would be a mean if the whole thing on the right-hand side here were just theta. It would be the mean over the partitions. But instead, we're going to censor at some chosen value lambda, and then we're going to add noise. How much noise? Well, it depends how much privacy we're willing to leak here. And also, instead of the number of observations, it's the number of partitions. So we need a lot of data to do this. And we'd like the number of partitions to be large because that will reduce the amount of data. Lambda, we have the same Heisenberg uncertainty kind of issue here. So that's sort of the trick. Then we're going to have bias correction. So let me show you what it looks like. This is the same equation, no big deal. Okay, now I'm going to give you a visual version of how we do a bias correction. This is the distribution of the uncensored estimators. We would really like the mean of those because that's pretty much the same thing as just taking the entire data set, applying our estimator like we would have done previously. We could have, of course, previously taken our data, divided it up into 10 categories, estimated whatever we did and taken the average of those. That's this thing. That's what we want. But we don't get to see that because we have privacy violations. First, we censor. The simple version of censoring is just censoring from the top. So we have the censored distribution of these things, and we don't know when something was censored or when it wasn't. The orange thing here is the censored distribution. We do know, by the way, that the uncensored distribution is normal because that's the central limit theorem. It actually works, right? But once we censor it, it's a censored normal, so a bummer. The area under here, this is something we know, right? It's alpha, so it's the integral of this normal, of the underlying normal to the right of the censored point. That's what this thing is. So it's the area under the normal. This is the same theta as over here. So it's an equation that has the goal in it, and sigma squared is the variance of this. It's the same theta and same sigma squared as over here. Okay, so that's what we want is this theta. Okay, what else do we know? Like, is there some way of us getting to theta? Like, how would we? It would be easy to get theta c, which is the mean of the censored distribution. That's pretty much what this will give us, right? But we don't want theta c. We want theta. How do we correct for the censoring? Well, there's one other thing we know, which is this theta c is a combination of the mean of the truncated distribution, which is everything except for the spike there, times 1 minus alpha, plus the censoring point times alpha. So it's the weighted average of those two things. So we know this equation and we know this equation. So what does that mean? That means we have two equations, great. But unfortunately, we have 4 unknowns. And remember, we only want theta, but we got all these other unknowns in there. So what are we gonna do? Well, first thing is we're going to disclose this by, in other words, we're going to estimate it with this, right? Because this is our estimator. We can actually do this. We're allowed to do this under differential privacy. That gives us an estimate here. And so now we only have three unknowns. Then we, whoops, sorry about that. Then we can also disclose alpha. That gives us two unknowns. So now we have two equations, two unknowns, and so we just solve them and we get an estimate of theta. So we start off with in every partition, we estimate whatever we wanted to estimate. We then censor it. We then add noise. We then use this equation, which gives us an estimator, but it's biased because of the censoring. We then correct the bias with this, and we now have a bias correction. Now I'm going to give you one more, the last page of complicated math, which is how you estimate the variance of this thing. Well, there's two unknowns there's two things that we estimated, which is this mean, and which is whatever quantity you cared about, and also the area to the right of the censoring point. We know that this is true, and it turns out that these are functions of the disclosed parameters. You can use standard clarify-like simulation approaches to take these, stick them in here, and get the quantities that we care about. This is the bias-corrected quantity that you care about. The standard deviation is the standard deviation over the simulations. The bias correction turns out to reduce bias and variance. Okay, so that's the math behind it. It enables you to take pretty much any estimator and get a differentially private version of it that you can say guarantees the privacy of your respondents, and but you can also get appropriate standard errors for that, and there'll be no bias for your calculations. The great thing is that you can then go to a government agency or a company and say, give us the data. We can guarantee mathematically that your customers or your citizens will not have their privacy violated. Guaranteed. Not that we'll try hard, but guaranteed. And then we have guarantees as social scientists that our analyses will make sense. So just quickly, in practice, this is what it looks like. All simulations ever conducted in papers always confirm the author's conclusions, and these do as well. And so the vertical axis is bias, where there's zero bias up here and more bias as you go down. Obviously, as this is the amount of censoring. As the amount of censoring goes up, the uncorrected estimate has more and more bias, but our corrected estimate has essentially zero bias the whole time. If you do it based upon the sample size, it gets a little more noisy as you have fewer observations, but pretty much there's bias if you don't correct, and there's no bias if you do correct the way we suggested. Similarly, a third one, also bias on the vertical axis, zero up here, more bias going down here. If you decide how much privacy you're willing to leak, no matter how much privacy you're willing to leak, there's going to be bias because they're censoring, but not if you correct. And finally, our standard errors, they're true standard errors in our simulation, is going to be this gray value here, and the estimated corrected standard errors that we have here are almost the same thing there. And then this is uncorrected, which is even worse. So and then I'll show you all four just because I get to dwell on them a little more, but not for any good reason. So last page, we're going to switch from a data sharing regime to a data access regime. Differential privacy protects individual privacy. It enables inference to the private database, not the population. Unless you do what we described. It's usually biased. There's no uncertainty estimates. It fails to protect society, even though it's protecting individuals from fallacious scientific conclusions. But with inferential validity, we can fix these things. A scientific statement is not necessarily one that is correct, but it is one that comes with known statistical properties and valid uncertainty estimates. That's pretty much our responsibility as researchers. We have to, whatever numbers we give have to have known statistical properties like unbiasedness or consistency or something like that. And we have to say how uncertain we are by providing standard errors or confidence intervals. And now we can do that with privacy protected algorithms. This proposed algorithm is generic. Most statistical methods will work. It's statistically approximately unbiased, has lower variance, valid uncertainty estimates, computationally efficient, solves political problems technologically, and there's a bunch of implementations at different stages. We have, there's a version on the web which you can get in R. There's a version from Facebook that works on their servers. There's a collaboration we have at Harvard with Microsoft, and this is the Institute for Quantitative Social Science that I run. We have a project called OpenDP, where you can look at opendp.org, which is open source differentially private software that we have lots and lots of companies and governments and the whole field really is working on developing open source differentially private software so that everybody can use it. You can go to my website /privacy and you'll see these papers and software and slides and some videos. This is the paper that most of which I described today with Georgie Evans, who's a graduate student of mine, and Meg Schwenzfeier, who's also a graduate student of mine. She just finished being Joe Biden's chief data scientist in the 2016 election, and Aberdeep Thakurta, who's at Google. There's a paper coming out in the AJPS on differentially private survey research with some of those people, and also Adam Smith, who was one of the original inventors of differential privacy. And another paper coming out in political analysis, which is exactly how to analyze the Facebook URLs data set. I'll mention one more thing, which is the Facebook URLs data set is very close to the United States, the way the United States Census is releasing their data. The United States Census Bureau went back and took, they do a census every 10 years. They took their 2010 data and they did a privacy attack on it. They went to see, could we re-identify anybody from the 2010 census? It turns out they were able to re-identify, provide the individual survey, the individual census responses of approximately 75% of Americans by attacking their 2010 data. So when they released the 2020 data just this past August, they released it in differently private format. So anyone that analyzes the U.S. Census from now on, or the 2020 U.S. Census, is going to have to deal with methods like these. So I'd be thrilled to take your questions.
Thanks so much, Gary. It was a fascinating talk, and now we'll take questions. And let's start with the Zoom room. And I think I'll pause first.